institutions. And now let me move on to our first talk. Our first talk is going to be given by Yu Xinding from Penn State University, and his talk is titled Lightweight Lidar-Based Centralized Cooperative Localization Model for Leader-Follower Automation System in GPS-delayed environments. Okay, that's a really great topic. I mean, there are some terms that I really like to learn from this presentation. All right. So Yuxin, now the room is yours.
Can you hear me?
Yes.
Okay, so let's share my screen.
Yeah, all right.
I need to share the uh
Did he just dropped out? All right, he's rejoining.
okay. It seems that I cannot share my PowerPoint. And
Oh, you are, yes, we need to make you as a host.
okay.
Oh, I can't do it. Donya, can you please, who is the host, Mohammed? Can you please help make sure all the speakers are co-hosts in this session? Now you are the co-host. Are you able to share?
Sure, I can do.
Okay. Now maybe if you can see my PowerPoint right now.
Yes, that's perfect. You need to now presentation mode.
Now it's good.
Yes, perfect.
Okay, so hello everyone. I'm Yuxin from Penn State University. Today's presentation is about the lightweight lidar-based cooperative localization model for the leader vehicle. Leader-Follower cooperative driving automation system during GPS-defined environments. And so now I'm talking about the background of our research. So autonomous driving technology bring about a huge revolution in transportation area. While we know that autonomous driving is a broad topic, so here we just focus on the Leader-Follower cooperative driving automation system. And the problem here is that in this system, the relative position information, like where each agent in this system is very important for the operation of this system. So, and now we always use the GNSS to provide this information. While sometimes you will lose your GPS signals, and sometimes your GPS signals is not reliable, like during mountain area. So here, we want to do is we want to make a model to keep providing this position information even you lose your GPS signals. Yeah. And here I will use the ATMA system to explain what is the Leader-Follower cooperative driving automation system. So as you can see here, the ATM system is used to ensure a safer environment for the DOT workers when they do like essential tasks like striping or stuff like this. As you can see, you have two trucks, and the leader trucks will handle these tasks, and the follower trucks will like act as a safe buffer to in case of accident happen. So if you use this system to replace DOT workers, maybe you will decrease accident happens in the highway or place like this. So you will get two trucks, and the follower truck will just follow the leader truck, and the leader truck will do these tasks. Yeah, so that's the ATMN system. And so in this research will I will consider this research as a cooperative localization problem. So within the leader-follower cooperative driving system. So now I will quickly talk about the literature review. So in the current literature, articles on cooperative localization can be generally be categorized into two types. So one is the agent to infrastructure based methods. So these methods use relative position information exchange between vehicles and the base station along the road to ensure constant communication and the data exchange. So basically you will get a base station, and the communication process will provide between the base station and your agent will provide each agent within the multi-vehicle system the location information. While the gap here is pretty straightforward, is that the coverage of this base station is limited. Like in mountain area, you cannot say build the base station here, right? So another one is agent to agent based methods. And these methods depends on the interaction between the agents to get the relative information. For example, like if you can use a camera, the camera can directly get the other vehicle's location, like if you can use your like computer vision algorithm, right? And another way is that you can use the cooperative SLAM, like the simultaneous localization and mapping algorithm, cooperative SLAM algorithm to do this, right? While the gap here is, as you can see here, the gap here is that every vehicle needs to transmit the, say, the camera data or the LiDAR data, and the communication channel, this will burden the communication channel. And another problem is that it requires a lot of computational resource, which means that you cannot run these methods in real time. So if you want to use these things in your, like, say, ATMA system, you have to make sure that it can be used in real time, or right, you cannot use these things to localize your vehicles, right? So yes, so in this research, we want to solve these two problems. Firstly, computational expensive problems, and secondly, we want to have a comparatively higher accuracy, like using our proposed model. Yeah. So now I will come to the methodology part. We will use the agent-to-agent methods framework to build our own model. And to facilitate the description of each module in this study, we focus just on two vehicles. So here we just use two vehicles, one leader vehicle and one follower vehicle, to demonstrate our proposed model. So as you can see here, each vehicle will be equipped by LiDAR sensors and IMU sensors, and we will use this sensor data to localize the leader and follower vehicles within the leader-follower system. Yeah. And so firstly, I will talk about the feature extraction module. This module is used to decrease the size of the LiDAR points cloud, because LiDAR points cloud is very big, and this will decrease the running speed of our system. So yes, so as you can see here, firstly, I will remove the distortion of the LiDAR point, because when your vehicle keep running, the LiDAR will have the distortion. For example, LiDAR send the points out at this place, and this vehicle will not stop. And then when these points get back, when you get back these points, the vehicle will go another place, which means that the shape of the LiDAR points is not right. So I use this equation to remove the distortion. I will not go into this equation due to the time limitation, but I use the IMU to help me remove the distortion. And after that, I will use the voxel to I will divided the point cloud into individual voxels by extracting the geometric features from these voxels. I preserve the original characteristic of the point cloud while I reduce the point cloud size. Yeah. And after that, I will go to the map construction module. So in this module, a container known as a feature map is established. However, it is not a conventional map. It only contains described LiDAR point clouds from the leader vehicle and their corresponding poses. So you can think of this dictionary. You can think about this as a dictionary in Python. So where the index of each frame index is the frame number of the point cloud. The purpose of establishing of this container is to establish a relative pose relationship between the leader vehicle and the follower vehicle, thereby achieving precise localization, right? To obtain the pose over each frame of the point cloud, we use the KISS ICP algorithm on the leader vehicle, which is the state-of-the-art SLAM algorithm in the SLAM field. And this map continuously updates as the leader vehicle moves. These equations demonstrate how we update these containers, as you can see here, right? So basically, in this map, you will get some feature map point cloud and its corresponding pose. The pose here, you can think about the pose here as a location, and yeah. And then I will go to the follower vehicle pose estimate because I just estimate the leader vehicle's pose, and then I want to estimate the follower vehicle pose. So follower vehicle's prior pose. So after using the KISS algorithm, after using KISS algorithm, I get the leader vehicle's pose, and then I want to use NDT algorithm to get the follower vehicle's pose. So at this stage, we want to use NDT algorithm. While this algorithm requires a lot of computational resource, to reduce this source requirement, I use the initial guess I have to use initial guess for this algorithm. So we use IMU to estimate the rotation and the translation of the follower vehicle. So if you want to know how the follower vehicle move, you have to know the rotation and the translation. So for the rotation, I already get the rotation because when I remove the distortion, I already get the rotation here. The R matrix is the rotation of the follower vehicle. And for the translation, I just use the translation of the previous frame as a translation of this frame. So then after getting the rotation and translation, we get the transformation matrix, as you can see here. So next, as you can see here, this is a transformation matrix. And after this, we can use this transformation matrix to calculate the initial guess of the pose for the current frame of the follower vehicle. And the initial guess is then used as the input for the NDT algorithm to reduce the computational resource, right? And finally, we establish a graph optimization module to eliminate the accumulated errors during the operation. So this algorithm optimizes the vehicle's position at each moment by constructing a graph. In this graph, the nodes represent the pose or the location of this vehicle, and the edges represent the geometric constraints between two poses, which are transformation matrix I just calculate. And the red edges are calculated by KISS algorithm, and the purple edges are obtained from the post estimation module. You just see this module, right? And next, we establish a time constraint module. The purpose of this module is to ensure that all components integrate well and maintain the system real-time performance. For example, the computation time of the entire system algorithm needs to less than the LiDAR's frequency. This means that when the next frame of the LiDAR points enters the system, we must ensure that the entire system has already completed the localization of the previous film, right? And since there is currently no open source dataset for LeaderFollower operations, we use a Kala simulation platform to validate our algorithm, and we use 3 different environments, the urban area, rural area, and highway area, as you can see here, 10, 10, and 7, and 6. And you can also see some parameters of our LiDAR and IMU sensors, and the time headway of the LeaderFollower vehicles is 2.5 seconds. And here we can see some results for all environments, and for both leader and follower vehicles, the localization accuracy has improved compared using if you only use single SLAM or other cooperative localization methods in the literature. Our accuracy has increased by an average of 15%. Yeah. And the experiments had also demonstrated that our algorithm meets the real-time requirements. So the whole process, the whole framework of our proposed model just needs 192 milliseconds, and which is less than the frequency of our LiDAR. And yeah. So finally, in this research, we introduced a cooperative localization model for the LeaderFollower CDA system, designed to provide a stable localization in GPS compromised environments. And the results shows that our algorithm not only reduce the accumulative error, but also satisfy real-time requirements of the system. Thank you. That's all. Yeah.
All right, thank you, Yuxin. And let's see if you have any questions. Well, okay. Yeah. So this is well, I mean, now it looks like to me it's like a model.
Yeah.
It's a model. Have you tested this in any like physical environment?
Because no, not right now, because we need 2 vehicles, right? A leader vehicle and a follower vehicle. So it's hard for us to find this. We just have 1 vehicle, so yeah. So
Okay, yeah. So yeah, because you are I think that okay, now we have somebody Lee, you can just turn on your mic to ask.
Hi there. Thank you for your presentation. I had a question about potential failure modes. So it sounds like, you know, your work is trying to assist with these GPS compromised environments. And so losing GPS signal would be a type of failure that these vehicles could undergo. If companies were to switch to using your approach and your modeling approach, what types of failure modes could they expect? What types of assumptions are you perhaps building into this model that might impact the response times of these vehicles, or otherwise kind of impact the safety of their operation?
So you ask what types of failures may happen, right?
Yeah, so I guess building this relationship between a leader and a follower vehicle and building that around your model, in what ways might your model fail, or what kind of extra safety considerations would a company have to think about if they switch to using your approach?
And we have an potential failure here. So we do this research mainly focus on the ATM system. So we want to using this our proposed model firstly in the ATM system. So the thing here is that you can see if you met say a traffic light, right? So if the leader vehicle just cross the traffic light while the follower vehicle just met the red light, just stop here, and then you will get some problem here, right? And now if the travel distance, if the distance between these 2 vehicles is too long, and then you will not lose your communication between these 2 things, and then yeah, the follower vehicle will just don't know where it should be go. Yeah.
Okay, so following distance would become really critical.
Yeah.
Thank you.
Yeah, thank you.
And Yixin, we have one more question from the chat box. How many follower vehicles are optimized for this test for your modeling?
So as I just mentioned here, so for this paper, I just used 2 vehicles to describe our model. But actually, if you want to use this proposed model in, like, say, 1 liter vehicle and multi-follower vehicles, that's okay. Yeah, that's also okay. So here I just use 1 follower vehicle. Yeah.
All right. Okay. Sounds good. Thank you. Thank you, Yixin, and that is great. Now let's move on to our next talk. Mohammed, are you able to find I'm not sure whether the second speaker is already in the room. Are you able to find the recording?
Yes, the recording is ready, Dr. Liu.
All right. Okay. All right. Then let me introduce our next speaker. All right. Our next speaker will be Raja Prasad Rochohori, and he is currently assistant professor at the Heritage Institute of Technology, India, and he is also pursuing his PhD degree from IIT India as well. And his talk is about determination of the dynamic PUC value of E-Rickshaw in the traffic stream under heterogeneous traffic condition. All right, now let's just watch the recording.
The recording is not done in a format that is supported by Zoom, so I'll just present my screen.
All right. Oh, we can't hear. There's no audio.
And
all over the world is other things. Now, in this study or in this research work, we made an attempt to find out the PCU value of E-Rickshaw, which has gained much popularity in the suburbs of West Bengal, which is a state in the country of India. Now, the data that have been collected is from Jhargram town in West Bengal. There are many methods to determine the PCU value, but here we have used Chandra's method and time headway method. And Greenshield's model have been used to find out the capacity. Here I have just
We are losing the audio again, but it's probably you turn off your mic, so.
to congestion, and it is very popular, especially for short trips. It's an economical one, and it's an economic mode of transport that provide much comfort to the fellow commuters. Now, there are different methodology for determination of PCU value. Here I have mentioned some of them, but we have used the Chandra's method and the time headway method for the determination of PCU value of E-Rickshaw. Here, Chandra and Kumar in 2003 proposed the following equation for a vehicle type, where it states that the PCU of the vehicle type I is equal to the multiplication of the mean speed of vehicle type I divided by the mean speed of the car. The total is divided by the actual projected rectangular area of vehicle type I and the projected rectangular area of car. In the later half of my work, we have used this Chandra's method, and there I have proposed all the projected rectangular areas of the vehicle types. Now the method based on relative delay. Now for multi-lane highways, PCUs were based on the relative delay due to trucks. So the PCUs for the multi-lane highways based on relative delay may be found by the following formula. The time headway method is very, very important. Time headway is what it is defined as the corresponding time between two successive vehicles in the traffic stream as they pass a point on the road. Now, based on this interpretation, the model of PCU for the truck can be obtained by the following formula given on the left hand side of the screen. PCU of truck is equal to H mix, which gives you the average time headway between two vehicles in mixed traffic stream, divided by the average time headway between two passenger cars, minus the proportion of passenger cars in the mixed traffic stream, the total divided by the proportion of passenger cars in the mixed traffic stream. However, this formula is limited to some extent. The application of this method mentioned is limited to the case where the car and one or more vehicle is present in the traffic stream. Now, to overcome this limitation, a modified formula have been proposed that is provided on the right side of the table. The Permanent International Association of Road Congress proposed a model called homogeneous coefficient of a vehicle category present in a mixed traffic stream, where the speed as well as length of a vehicle were considered to formulate the homogeneous coefficient that is given in the following formula. Now here I have provided the details of the study area. It is in the Jhargram district of West Bengal in India, and the data were taken from the road between College Mode and Settlement Mode. Actually, the term mode means crossing over here. So the data collected between College Mode and Settlement Mode, as shown in the picture that I have provided here, it is a part of a state highway, which is nearly a straight road section. Now, the basic considerations that is being considered while selecting this site was it should be free from the effect of intersection, passed up, parked vehicles, curvature, gradient, and any other friction. The section has wide in proportions of different categories of vehicles. That means it has a wide and a mixed category of vehicles, and E-Rickshaws have just started operating in the past few years. Now the field data collection, the equipment used was drone because the method used was video photographic by drone. And I have shown a snapshot of a 30-meter trap length that was marked, and the flying height of the drone was 24 meters for this study. The recorded videos were collected and prepared for data extraction. Now the video data were extracted manually by playing the recorded video in the computer screen. A screenshot of how we have calculated or how we have extracted the data is being shown in the following picture. Now, the aim of the data collection was to get information on traffic volume, vehicle composition, and speed of the vehicle type, along with the roadway geometric characteristics. Data has been extracted for 1 minute interval and 5 minutes interval. The extracted data are classified into traffic volume, traffic composition, space mean speed, and time headway. Now, in all these data that we have extracted, in all these tables that we can see that in this classified traffic volume, I have given table classified traffic volume 1 minute interval from settlement mode to college mode. I have given a sample. I could not provide the whole data or whole table because there are huge amount of data that is being extracted from here. So traffic volume refers to the categorization and analysis of vehicular traffic based on different classes or types of vehicles such as car, trucks, etc. Now, all the vehicles in the traffic stream on the selected study area were categorized as car, big car, e-rickshaw, motorized two-wheeler, bicycle, cycle rickshaw, motorized three-wheeler, light commercial vehicle, and bus. See, on the left-hand side, in the time, we have 10:30 to 10:31. That is, we have taken data for 1 minute interval. So these are the traffic for a sample data for the traffic volume count for 1 minute interval from settlement mode to college mode. Now I have provided with a traffic composition which shows on the left hand side the number of vehicles and the percentage of vehicles that is occupying the road from settlement mode to college mode. On my previous slide, I have shown the traffic composition of the study section from settlement mode to college mode. And now I am showing you the traffic composition of the study section from college mode to settlement mode. On the left hand side, we have the number of vehicles, and on the right hand side, we have I have shown the percentage of vehicle types that is occupying the road from college mode to settlement. The speed of each individual vehicle have been calculated by taking its entry and exit times from the track length, which is the time needed for it to travel the 30-meter length. The space mean speed of each class of vehicle has been calculated by dividing the track length by the amount of time needed to cross the segment. Here also, I have given a sample data of the space mean speed represented in km/h of the study section from the settlement mode to the college mode. Next is time headway. Now, time headway refers to the time interval between two consecutive vehicles as they travel along a road. Time headway indicates vehicles which are closely spaced that can lead to higher traffic density and potentially contribute to congestion. Conversely, or on the other hand, a longer time headway allows for more space between vehicles. Now, the average time headway represented in seconds from college mode to settlement mode. As because we have taken a huge amount of data from college mode and settlement mode, in some cases I have provided the data from settlement mode to college mode, and in some places I have provided the data from college mode to settlement mode. Because there is huge amount of data which was not possible to provide here each and every detail. Otherwise, the presentation would have been much longer one. So while coming to the data analysis, in the Chandra's model, we found that the area of different types of vehicle were needed. So the present table shows the ratio of, or the area ratio of different types of vehicle. The proposed area of different type of vehicles are shown in the following table. And as a reference, we have taken Indo HCM 2017 and the paper from Majumdar and Jash in 2015. So the following table shows the proposed area of different type of vehicle. Now it's time to find out the dynamic PCU values. Now here we have considered the passenger car as the standard vehicle. So in the PCU values obtained by Chandra's method from settlement mode to college mode, you can all see that the time interval we have taken is of 5 minutes, and the car we have taken as standard vehicle, hence all its values are 1. And then by Chandra's method, we have calculated the PCU values of the different type of vehicles. Earlier I told that we will be finding out, or we will be using the Chandra's method and the time headway method to calculate the PCU values. So in the previous slide, I showed the dynamic PCU values calculated from Chandra's method. Now, this table shows the PCU values obtained by the time headway method from college mode to settlement. In my previous slide, I had shown the PCU values obtained by Chandra's method from settlement mode to college mode. So, in the next table, in the time headway method calculation of PCU values, I had taken a sample data from college mode to settlement mode. As we have taken car as a standard vehicle, here also the value of PCU for car remains 1. Now these are the different PCU values of different type of vehicle using Chandra's method. Now for car, big car, E-Rickshaw, two-wheeler, bicycle, cycle rickshaw, three-wheeler, LCV and bus, we have provided the maximum and minimum values of PCUs from settlement mode to college mode and from college mode to settlement. I have made prominent the value of E-Rickshaws as because we are aiming to find out the PCU value of E-Rickshaw. The previous slide showed the PCU values of different type of vehicle using Chandra's method, and the following table in this particular slide shows the PCU values of different type of vehicles by time headway method. Here also, I have made prominent the part of E-Rickshaw, which shows the PCU values of E-Rickshaw from college mode to settlement mode and settlement mode to college mode. Next comes the determination of traffic volume. The PCU values that were estimated were multiplied by the number of vehicles of that type, and those were added to obtain the total traffic flow in PCU per 5 minutes. This traffic volume was presented in PCU per hours and obtained by multiplying it with 12. So the sample study or the sample estimation of traffic volume estimated from settlement mode to college mode is provided in the following table. Determination of traffic volume continued. As in the last slide, I have shown the estimation of traffic volume from settlement mode to college mode. The following table shows the traffic volume calculation from college mode to settlement mode for a time interval of 5 minutes. I am telling repeated times that I have taken a sample of data. I have not taken the total data because it is not possible to provide each and every data here. Now, traffic density. Now, the traffic density was estimated by dividing the traffic volume with respect to the mean speed of the car. Now, the following table shows the traffic density from settlement mode to college mode for an interval of 5 minutes. This slide shows the table of the estimated traffic density of college mode to settlement mode for a time interval of 5 minutes. Now, this research work, or we have adopted the Green-Schultz model for estimation of capacity. The speed density plot helped us to determine the free mean speed and the jam density. These were used to establish the free speed flow model and estimation of capacity. Now here, I have shown the graph between speed and density, or in other words, I have shown you the speed density relationship from where the free mean speed and jam density were being found out, and the capacity from settlement mode to college mode was found to be 550 BCU per hour. So this shows the vertical curve of speed volume for settlement mode to college mode from the data that we have received by Chandra's method of calculation. Estimation of capacity from college mode to settlement mode. From here, I have shown you the theoretical curve of the speed volume from college mode to settlement mode from the data extracted by Chandra's method and the speed density relationship. From where here we get an estimated capacity of 573 BCU per hour from college mode to settlement mode. Last two slides, I had shown you the estimation of capacity by the data that we got by using the Chandra's method. Now in this slide, or in the next slide also, I will be showing you the estimation of capacity from settlement mode to college mode and from college mode to settlement mode using the data that we have received from the time headway method calculation. Here also, I had shown you the theoretical curve of speed volume and the speed density relationship, from where we have got the capacity from settlement mode to college mode as 539 BCU per hour. But please do remember, sir and madam, that this is from the data extracted by using the time headway method. Now the estimation of capacity by from college mode to settlement mode using the data from the time headway method that we got. Here also the speed volume relation and the speed density relationship is being shown, and from the free mean speed jam density, the capacity was calculated as 592, which is we have taken as a whole as 593 BCU per hour. In this following slide, I had tried to show you the variation of the BCU value with traffic volume that was extracted by using the Chandra's method. So the BCU value and the volume we have plotted, and these are the results in front of you. Last slide, I showed you the variation of BCU value with traffic volume using the data that we have got from the formula of Chandra's method. Now, the same thing I am shown, but the data we have received, or the data with which the BCU value and the volume graph have been plotted, is from the formula or the data we got from the time headway method. The following slide shows you the variation of BCU value with traffic volume. In my conclusion part, it has been observed that the BCU value of E-Rickshaw was varying from 0.78 to 1.15 when we are using the Chandra's method. but the PCU value varied between 0.77 and 1.12 while using the time headway method. Here, majority of the road portion was being occupied by motorized two-wheeler, e-rickshaw, bicycle, and standard car, and the percentage of bus, big car, and LCV were less. It has been observed that the speed density model has been fitted well with the field data having R-square value of 0.78 and 0.79 for both lanes when Chandra's method for PCU value calculation was done. The R-square values of speed density model are 0.81 and 0.79 for both lanes when the time headway method for calculation of PCU was done. From the estimation of capacity, when you use Chandra's method, we found that the capacity of both lanes were 550 and 573 PCU per hour per lane respectively, and the capacity of both lanes were 539 PCU per hour per lane and 593 PCU per hour per lane when the time headway method were used for determination of PCU value. Now, in this context of modern urbanization, the rapid rise of electric rickshaws, commonly referred to as e-rickshaws, has introduced a new dimension to traffic engineering and urban mobility planning. They are eco-friendly, cost-effective, which provide a very viable alternative to traditional modes of transportation. Now, what are the scope of the future work? Now,
All right, thank you, Mohammed, for playing this. And we are just going to skip the last slide. And I think this presentation has shared some information about estimating the PCEs. I mean, I think in our highway safety manual, it's called PCE, passenger car equivalent value. So I was really wondering about PCU. What's PCU? So CPU. Anyway, all right, let's move on to our next speaker. And if you do have any question regarding that presentation, just feel free to reach out to the presenter whose contact information is available in the chat box. All right, our next talk is titled Modeling the Operation on Labor Cost Autonomous Robotaxi Services, given by Lee Kapla. Well, I kind of forgot. I think you shared with me the bio information and yeah, from George Washington University, and I don't remember you are still students or not students. But anyway, I'll let you to introduce yourself. All right, Lee. Now the time is yours.
Yeah, well, thank you so much. The big update for everyone. I defended my dissertation yesterday successfully. So this is my first presentation that I get to call myself Dr. Kaplan, which is very exciting. Thank you all for being here. But yes, I'm a PhD candidate. Well, I don't know what that classifies me as, but I'm at George Washington University in the Department of Engineering Management and Systems Engineering. And thank you all for tuning in to be here today. I'm sure that this presentation will be just as exciting as all of the Olympic events that everyone has been tuning into. But today I'll be talking about autonomous vehicles being operated as a passenger transportation service, what I call a Robotaxi service. And there's a lot of excitement about how these different services could potentially improve our transportation systems. Also, a lot of concerns about potential negative impacts. But as these different services are starting to emerge in different cities, it's an open question whether or not they are technologically performant, but also whether they will be economically viable. And at the same time, there are a lot of discussions going on right now about potential negative labor impacts, these fears about widespread job loss for drivers working as taxi drivers and ride-hailing drivers, and also drivers in other transportation sectors. So to try and get at some of these questions, researchers have been developing cost models to try to understand how different types of autonomous vehicle services might compete with existing modes. But these prior cost models have lacked precision in two key areas. The first are the labor costs. A lot of prior studies have assumed that you're getting rid of that driver and suddenly you have zero labor costs. But automation tends to change the work system and introduce new types of jobs to support that technology service. So it's not necessarily true that you're getting rid of all of your labor. And the second big assumption is the cost to automate a vehicle. A lot of prior studies have used technology costs of around $10,000, and that's based on Tesla's original proposed cost of their full self-driving suite. But Tesla doesn't use Lidar sensors, which are a higher cost sensor, and the companies that are operating right now, like Waymo and Cruise, do all use Lidar sensors. And a lot of experts feel that Lidar sensors are essential for safe autonomous vehicle deployment. So in our study, we considered additional labor and technology costs to revisit this question about how robotaxis might compete with traditional taxi services, and then also did a little bit of scoping about what those potential labor impacts might be. We did this by developing ground-up cost models for a traditional taxi service and a robotaxi service, calculating a fare per mile value for both. This fare per mile was composed of a lot of different individual cost components. For our robotaxi model, we had a separate cost for that additional technology financing cost, and then had different labor costs for the two different types of services. Because we were calculating things on a per mile basis, we had to assume an annual mileage, which we assumed would be 65,000 miles per year, based on the average mileage of a New York City taxi. Now, when we talk about labor, we bounded our analysis to only look at roles that directly supported the robotaxi service, the taxi and robotaxi services. So not considering additional labor involved in technology development, AI model training. Those are important things to think about when looking at the big picture of that labor transition, but we were only looking at frontline labor roles as part of our analysis. Now, like all good modelers, we wanted to try and ground our model in real-world data as much as possible. So we used existing data on taxi services, their maintenance costs, fuel costs, etc., and also used a lot of those same assumptions in our baseline robotaxi model, and then accounted for uncertainty about how that automation of that vehicle would change those costs through two different ways, which I'll discuss on a future slide. Now, as I mentioned before, there were these kind of researchers weren't as sure about how automating these vehicles might change those labor roles. And there's not a lot of information out there about it. So we had to go out and find out what these emerging labor roles that are supporting these robotaxi services are and how much they cost. And we did that by first conducting direct observation of these services. There are robotaxi services available for members of the public in certain US cities. So we were able to do these observations, take rides, interact with these different types of workers. We also conducted observations of a robotaxi control center where some of these remote support roles are located, as well as observations of a robotaxi fleet depot where these vehicles are stored and maintained. We supplemented these observations with interviews with autonomous vehicle regulatory and operational experts, over half of whom either previously worked at or currently work at a robotaxi firm, so have a really good sense of what these roles are and the work that they perform. And finally, we triangulated our findings using archival data sources, getting job postings for some of these emerging frontline robotaxi roles, getting information about their wages, and also using public reports that these companies have put out that further detail their operations. Now, what we found through all of this detailed data collection work is that, in fact, robotaxi services do require human labor for a number of different roles. You're not just getting rid of the driver and then, as I said before, you're not having zero labor involved. So some of these roles, a field support agent is someone who is going to go out and respond if the vehicle gets a flat tire or is unable to continue its journey. Field support agents can provide that in-person response. You have customer service agents that are remotely able to answer rider questions or keep an eye on rowdy riders who might be causing trouble in the vehicles. Coordinators help to coordinate between these different roles that these companies are creating, helping with information processing and information sharing between roles. You still have mechanics who are taking care of these vehicles, though for the robotaxis, they're a little bit more specialized. They have to have knowledge about these sensors and computational equipment. Remote monitors aren't remotely driving the vehicles, but they are able to provide secondary assistance, secondary verification to the vehicles if they get stuck, or helping vehicles navigate more complex situations. Now, as I mentioned before, there's uncertainty about how robotaxi futures might unfold. And there's also variation in how services are used based on time of day, day of the week. So we accounted for this variation and uncertainty in two different ways. The first was by performing Monte Carlo simulation. So instead of assuming a single input value, we're drawing inputs from distributions. And the second is by performing scenario analyses, considering 4 potential robotaxi futures. In the advanced tech scenario, we're taking kind of an optimistic view, saying that as this technology improves, that technology cost is going to decrease. It's going to decrease some of these other operational costs. And perhaps the vehicles will run into fewer problems and you'll need fewer workers to support them. In the high usage scenario, we're considering potential dual use of these vehicles, which is a business model that a lot of these firms are exploring. So transporting not only passengers, but also goods, kind of your Uber and Uber Eats type model. And so if you can have that increased utilization and mileage, we assume you might have a slightly shortened vehicle lifespan. The medallion system scenario is thinking about regulatory impacts. In the United States, taxis and TNCs, ride-hailing companies like Uber and Lyft, are actually regulated differently. And taxis sometimes have to pay for high-cost medallions. So in New York City, a taxi medallion can cost over $100,000. So if a robotaxi firm has to buy a medallion, that could introduce another high cost. Finally, in the lower density city scenario, we're considering potential operation of robotaxis in different types of geographic areas. They perhaps might have decreased capacity utilization and mileage if they're operating in a lower density city, but that might also mean that you have a more increased vehicle lifespan. On the next slide, I'll present the total costs from these models, the models for the status quo taxi system, our baseline robotaxi model, and then the models for these 4 different scenarios. In this plot, as I said, we're showing total costs by category, but then also breaking down those costs by each individual type of cost component. And what we can see is that light blue bar that's on the far left for all of the plots is the biggest bar for all of these different scenarios. And that light blue bar is the labor cost. So what we can see clearly is that labor remains a key cost component for all of these scenarios. We can't be ignoring those labor costs. Now, at the same time, we can see that indeed the labor costs for the different AV models are much lower than for that of the non-AV taxi. And instead, we see some of those costs shift to that orange chunk, which are the technology financing costs. And what I'd also like to point out is looking at that $1 per mile cost value. a lot of prior studies assumed that total operational cost for robotaxis could be less than $1 per mile. What we found by doing this detailed labor cost accounting is that labor costs alone might be $1 per mile, let alone adding in these other costs. And so you really need to get to that more advanced technology future where you can bring down those technology costs and decrease the number of workers if you're going to try and get to that total cost of less than $1 per mile. Now, that said, once again, these are outputs from our models, and we find that overall, still the fares for the different AV robotaxi scenarios could be lower than that of a non-AV taxi. So that means that these robotaxi firms could outcompete traditional taxis based on price. And we did compare these fares from the taxi model to actual fare values that are available on public data sets and found that it did align with our model results. So that gave us some confidence that we were capturing these costs correctly. We also performed a systematic sensitivity analysis and found that our models were most sensitive to capacity utilization, annual mileage, and different labor ratio and labor cost values. So we took a little bit of a closer look at these different inputs. Now, in these plots, we're showing how fare per mile changes based on changes to capacity utilization and annual vehicle miles traveled. And we're only plotting the results from the taxi model, our baseline robotaxi model, and that optimistic advanced robotaxi model. The black points represent the input values that we use in our models. And what we can see is the fares across the board are lower for those robotaxi models. And you could actually kind of move left and up on those different robotaxi scenarios, meaning you could deal with having a lower utilization, a lower vehicle miles traveled, and still be able to offer lower fares, or perhaps offer an equivalent fare as that taxi model, but not have to worry about having as high of usage. In this plot, it's a similar plot, but now we're looking at those labor ratios. So the points represent how many vehicles an individual worker would be responsible for. For that taxi plot, that point is referring to the number of vehicles a dispatcher would be in charge of. Obviously, you need a human driving at all times. And then for the baseline and advanced tech plots, those points represent how many vehicles a remote monitor would be in charge of. And what we can see in this plot is over on that left-hand side, it's really steep. So for every additional vehicle you can have that worker be in charge of, you're really going to significantly lower your costs. It's going to make a big difference, but it flattens out relatively quickly. And so once you get beyond around 15 vehicles per worker, it's not making a huge difference in terms of cost. If you can get that remote monitor to be in charge of 19 cars versus 27 cars. But where it might make a big difference is the impact to that worker and what their cognitive overload might be, or how quickly they can respond if they're getting a call. And so robotaxi firms really need to think about these balancing, kind of trying to decrease costs and labor costs against still having safe and high quality services. Finally, as I said before, we wanted to think about potential impacts to the number of frontline worker jobs and also those worker wages. And so in this plot, we are showing the wage distributions for the number of workers, assuming an 100 vehicle fleet, and the labor ratios that we use in our model. Up at the top is the distribution for the taxi service. And we can see that it's a unimodal distribution with most workers making around $15, $16 an hour. As we move down into the second and third plots from the top, those are the baseline robotaxi model and the advanced tech models. We see that the total number of workers decreases by between 57 to 76%, but the wages shift slightly higher. We now have a bimodal distribution the larger chunk, most workers make around $19 an hour. And that second smaller bump is for the slightly more specialized coordinator roles that get paid slightly higher wages. Overall, our study found that, as we saw, labor remains a significant cost for existing robotaxi services. This is something that researchers should really be accounting for and including in their cost models. While labor is important, utilization rates and annual mileage will be the more influential factors potentially for robotaxi competitiveness. And if we see this transition from taxis to robotaxis, we might see the number of frontline jobs decrease, but could perhaps see associated wages shift higher. Now, we're only looking at a specific type of jobs, and there might be new jobs created in the technology development side or distribution. So this is the full job picture, but it is still an important thing to look at and consider. Thank you all for your time and attention, and I look forward to any questions you might have.
All right, Liz, thank you. That was really great presentation. I mean, before you look at all those questions in the chat box, there are so many. I'd like to say that I really wish my students are here in this session to listen to your talk. And because you have shared us with a lot of those numbers that we would like to have in our models for more choice modeling, because we need those costs and realistic costs. And currently we are to basically make a bunch of assumptions, but those assumptions not going through like what you are done, really sophisticated manner. All right, now if you can take a look at the chat box. So, well, I tapped some of them there, and so there's talking about the cleaning, just a little tiny detail, don't get every cleaned. There's a cost about cleaning. Do you have any insight about that?
Okay, yes, I see Martin's question. Yes, so we accounted for cleaning costs slightly differently for the taxi and the robotaxi models. In the taxi model, we're assuming that a taxi driver can take their vehicle through a car wash. And I have to double check the numbers, but I believe we assumed once per week, and then they can hand wash their own car, getting kind of the interior cleaning, picking up trash, and using a fairly inexpensive cleaning kit. So we use the cost of a cleaning kit and the cost of a car wash, assuming a certain frequency of cleaning for the taxi model. Now, a lot of prior studies, or some prior studies that did account for cleaning costs, made those same assumptions for the robotaxi. But what we found through our field work is that robotaxis have to be cleaned in a slightly different way. You can't run a robotaxi through a car wash because they have these really delicate sensors, at least how they're designed right now. And so those vehicles are actually being cleaned by those field support agent workers. And so in our robotaxi model, we account for the cost of that field support agent who is hand cleaning the exterior and interior of the vehicle as part of their everyday work. And we assumed that the marginal cost of those cleaning supplies are relatively small compared to the cost of that worker. So we essentially bake in that cleaning cost as part of that field support agent labor cost.
Yeah, that makes sense actually to me. Our next one is the robotaxi collect fares only through apps or mobiles? Passengers with cash would prefer general taxi? That's about the payment.
Yes, that's a really good point that the individual brings up. As they are designed right now, at least for the companies operating in the US, they do use an app-based fare collection system. And so they don't have that way to accept cash payments, which is, an equity concern as well. There's potential for them to perhaps figure out other ways to accept cash payments in the future, but as designed right now, they only accept payment through cash. And so, as this individual is pointing out, it might limit the people that want to use that service, or even that are able to use that service, if someone doesn't have access to a smartphone or a bank account and can only pay by cash, then they might not be able to use these services right now. So yes, and then it would also limit kind of competition and mode switching.
Yeah. But there are just so many ways to make payments. I'm just thinking, but still every payment has some limitations there. Think about they can just use their face, the fingerprint, or just credit cards. All right, our next question is about the your estimates are based on the average yearly mileage as for traditional taxi, but AVs may have higher mileage. Do you think that is something you can think of, take under consideration in your research?
Yes, so we accounted for that in our high usage scenario. And yes, some researchers in their prior cost models assume that autonomous vehicles will have a higher mileage than traditional taxis. We chose not to use that in our baseline model because it hasn't been proven out yet. There could be reasons that they're not used as much. Right now, their domains are more limited because companies are still working on developing that technology and expanding their routes, expanding their operational areas. And also people might not want to use them as much. So we didn't feel that we decided not to include it in our baseline model because we didn't feel that was necessarily the ground truth, and instead accounted for higher utilization as part of one of our scenario analyses.
All right, that's great. Okay, hopefully you can be quick. On the last question is about how this business would affect the employment.
Yes, so as I said at the beginning, it's the potential job impacts is a big area of concern. As we found in our model, it could decrease the number of frontline worker jobs, which would potentially displace these taxi workers, both kind of drivers and dispatchers. And so that is an area of concern, whether displaced workers could move into these emerging robotaxi roles. That's, if they have any desire to do that, if they feel qualified to do that. It's an open question and something that I look at in actually a different one of my research studies. I saw Martin's comment in reply. There's this question about, well, we have a lot of labor shortages in areas of transportation. Can this help with those labor shortages? That's often discussed in the context of autonomous vehicles and trucking. But once again, these vehicles need to show that they are technologically performant, economically viable, and then we can also think about that labor piece as part of it. But it's something to keep discussing and exploring further.
Thank you, Lee. That was a really insightful talk and some questions and answers. All right, thank you so much. And now let's move on to our next speaker, given by Dr. Tianjia Yang, who is currently a postdoc researcher at Penn State University, and he received his PhD civil engineering from the University of North Carolina at Charlotte. All right, his talk is about transit signal priority. All right, Tianjia, are you now able to share your screen and start the talk?
Yes, let me share the screen. So can you hear me and see the screen?
Yes.
Okay. So I'm glad to have the chance to present my work about using deep reinforcement learning approach under the connected vehicle environment to control a traffic signal to achieve traffic transit signal priority strategy. And our work is published in Journal of ITS. And if you are interested in details, you can scan the QR code. And the presentation will be divided into 5 parts. First, I will introduce some background about transit signal priority and the connected vehicle technology and deep reinforcement learning. And the second part, I will briefly introduce reinforcement learning and I will details how we define the actions, the space, state space, and the reward. And the third part is about experimental settings, and followed by the results and some future work we plan to do. The first, I think you guys are very familiar with the figure in the right hand that it vividly shows that public transportation system is more efficient compared to private travel mode, and so it's affordable and sustainable mode, but it's less attractive to us because most of the time we have to share spaces with strangers, and generally we will experience longer travel time, and there are also there are other issues related make it less attractive. So so we proposed some strategies named as transit priority strategies, try to provide high quality transit services to the public. From the macroscopic level, it's including the formulating policies to develop transit infrastructures or providing subsidies. And our research focus on the microscopic level. We try to grant priority right away to transit vehicles that travel on the road. And for the traditional transit single priority, it generally causes some adverse effects to other traffics, especially the competitive traffics. And these disadvantages hinder its widely adoption in the real world. But with new technologies, the transit single priority research have great potential to progress. For example, if we use connected vehicle technology, we can obtain the real-time data of the vehicles travel on the road. And if we use the rapid advancement AI technology, we may develop smarter single controller. So my research try to propose a smart traffic single controller. First, leverage real-time traffic data that is available in the connected vehicle environment. And the second, we adopt AI technology, which is named as deep reinforcement learning approach to optimize the signal phasing and timing. And for the deep reinforcement learning, we designed a person-based reward function. And by using this reward function, we can ensure traffic performance based on passengers rather than vehicles. And in this way, we can ensure that the vehicle with more passengers can be granted priorities compared to those vehicles that only with one passengers. So for the reinforcement learning, I will not go to the details about the reinforcement learning, such as functions or something like that. But in a general reinforcement model, like what shows in the right hand, and it has an agent, and the agent interact with the environment. In my research area, the environment is the traffic is a traffic environment, including the vehicles traveling on the road, and also we have to consider the traffic configurations of the intersection. And the agent observed the current state, which is the traffic information at each time step. And based on the traffic information, he chose action based on the policy. The policy is a control law. We can consider the policy as a control logic inherent in the agent. He chose action based on the policy, and then the environment receives action and gives back reward to the gives back the reward, and also transit to the next state. And the agent iteratively updates its policy based on the reward. And at the end of the day, it can reach to optimal control policy. So this is general reinforcement learning. And in our research, we use a classical deep reinforcement learning algorithm named Deep Q network, which is short for DQN. And for the DQN, we just use the vanilla version. It has two different network. One is named as Q value network, and another is named as target network. And it also utilizes the replay memory. By use these two mechanisms, the deep Q network can stabilize the training process and avoid divergence. And the most important for our work is to carefully define the state space, the action space, and also the reward function. So for the state space, because we assume that our controller is implemented in a connected vehicle environment, so we use the real-time data of the from the connected vehicle. We choose the passenger occupancy and the speed, and also the location of the connected vehicles that approaching the intersection. And we use a method named as discrete traffic state encoding method to format this information into image-like representations, just like the picture shows. So for each approaching line, we discretize the line with the predefined length, and in this way, each line can be divided into several cells, and the data of each connected vehicle can be assigned to corresponding cells based on its location. And in this way, it can be formulated image-like input with two tables. One table contains the speed information, and one table contains the occupancy information. And for the action space, because we consider a typical four-leg intersection, so there are 8 different possible combination of non-conflicting movements. So our action space is 4 discrete actions. And for the reward function, we choose the cumulative personal delay differences between sequential decision steps as the step. So first, at each time step, we obtain the vehicle delay for each vehicle and the passenger occupancy for each vehicle, and then we can calculate the cumulative person delay for each time step, for each decision steps, and then we calculate the reward by the last step cumulative person delay minus the current step cumulative person delay. So in this way, actually the passenger occupancy acts like a weight for the vehicle. So more passengers on board, the will be considered more in this reward function. And for the experiment, we used a 4-leg intersection located in the east of Charlotte, and we used Zoomer to build this simulation test bed, and we also obtained the real world traffic volumes from Charlotte DOT, and we considered 2 different traffic demand. One is peak hour traffic demand, and one is off-peak traffic demand. And we can notice that those traffic demand is not balanced from across different turning movement. And to evaluate the proposed controller, we also built 4 different environments. Each environment corresponding to a traffic controller. The first environment is pre-time singular control environment, and in this environment we use the controller use pre-time singular control logic, and we use 4-phase program, and the singular timing are calculated based on Webster method. And in this environment, the buses and the cars are assumed as human-driven vehicles. And in the secondary environment, we use actuated singular controller to control the singular timing and phase. And the ring and barrier phase program is used, and also the bus and the cars are human-driven vehicles. And in the third environment, we consider that the buses are connected vehicles, but the controller is still actuated single control. But when the bus is approaching the intersection with the predefined distance, in our environment, we set it to 100 meters. So when bus approaching the intersection within 100 meters, then the controller will switch the signal to provide unconditional priority to the buses. So the last environment is our DQN single control environment. So in this environment, we use the 5-trend DQN controller to control the single phase and timing. And for the DQN, we use a convolutional neural network to process the input, because the input is an image-like representation. And other basic settings are, so we simulate 1 hour with a 10 minutes warm up, and the performance metric are averaged over 15 rounds with different simulation seats. And for the basic scenario, the basic occupancy is 3 passengers for bus and 1 passenger for cars. And bus arrival headway is 5 minutes, and the bus only travels in the north-south direction. And we trained 2 different agents for 2 different traffic demand. This is the general results that in terms of average delay, and we can notice that our DQN SC outperform other controllers in terms of average person delay in both peak and off-peak hours, and it also can significantly reduce the average bus delay, while also reduce the average car delay compared to the baseline, which is pre-timed single controller. And we look deeper that we compared the average vehicle delay in different turning movements, and the result shows that for those controllers not consider transit single priority, they can provide much balanced performance to across each direction. But if we introduce the transit single priority strategy, some turning movements such as the northbound left turn or southbound left turn may be sacrificed. So this may be our future working direction to make to provide more balanced service while ensure transit single priority. And we also did some sensitivity analysis, consider the connected vehicle market penetration rate, the passenger occupancy, and the arrival headway. So as we can imagine, when the connected vehicle market penetration rate increase, the performance in terms of both average vehicle delay and average person delay increase. And we can notice that the turning point in our experiment is that when the connected vehicle market penetration rate reach 40%, the performance of our controller can achieve a decent performance. And in terms of passenger occupancy, we can notice that with the passenger occupancy of the buses increase, the average bus delay, which is the blue line, decreased significantly, which showcases that our proposed controller can provide our priority based on the passenger occupancy. And regarding the arrival headway, our controller is insensitive to this factor. And the results demonstrate that the deep reinforcement learning, applying deep reinforcement learning in traffic signal control to provide priority is a promised research direction, but is still in the start stage. So for the future, we try to list several research directions. First, we consider to implement multi-agent reinforcement learning to control multi-intersection scenarios such as corridors or network-wide. And we also try to address transit operation challenges such as bus bunching problems, which is real-world transit operation problems. And we can consider more complex traffic conditions. In this research, we only consider that bus travel on south on the south northbound. But in the real world, there are some scenarios that the traffic controller may come across that there's simultaneous traffic priority request from perpendicular directions. So how to deal with that is also a problem. And also we can integrate traffic state prediction algorithm to make it more robust in low connected vehicle market purchase rate scenarios. And we all know that deep reinforcement learning is a black box, so it may output some catastrophic behavior, and for implemented in the real world, we have to avoid such phenomena. So we can develop a hybrid controller that maybe combines the strength of deep reinforcement learning algorithm with some baseline control rules to avoid such circumstances and ensure reliability. And thank you. That's all.
All right, thank you, Tianjia. Thank you for the presentation. And we have one comment and one question in the chat box. The first comment is, well, I like the person-based approach. And is there any other approach?
As I know, if we consider most of research just consider traffic signal control without provide priority to buses. So they only consider vehicle delay in terms of the person-based delay. So I think person-based approach is not that popular in our research area. And also for transit operation areas, there are also some research focus on to reduce the bus bunching problem, to make the bus arrive at stop on time. And in that way, they didn't consider the person-based approach also.
All right, thank you. Thank you, Rick. Next question, can you please answer very quickly? This approach would also work considering transit vehicles running late and prioritizing them correspondingly? Yes, I think
in our approach, we haven't considered this problem. So we just if the vehicle have more passengers, it may have more chance to grant priority. So we don't consider whether it's running on time or later or late. If we can achieve this goal by revise our reward function by, for example, introduce some on-time later running penalty or something like that to make it achieve that goal. And thank you for the question. That's a good question.
All right, that's great. Thank you, Tianjia. And now let's move on to our. Can you please start sharing?
Yes.
Our next speaker is Dr. Hannah Hook. who is currently a postdoc researcher at Ghent University in Germany. And she has a really diverse background. I mean, internationally diverse. He received his bachelor's degree from the Arizona State University, and he received a master's degree from the King's of College London, United Kingdom, and then he also received his master's degree from the University of Arizona, and then finally he received his PhD degree from the Ghent University. All right, Hannah, are you able to share your screen now?
Yes. I hope you can see it.
That's right. Yes.
And is it the correct view or the opposite view?
It's perfect.
Okay, great. Yeah, thank you for everyone who's still here for the last presentation of the session. I know it's a long block, so I'm glad that you're still here listening. I'm Hannah Hook. I'm a postdoc researcher at the University of Ghent, which is actually in Belgium, not in Germany, but close enough, so I understand the mistake. I'm presenting some research that one of my master's students did. She finished last year, but we finished up the work afterward to write it into a paper, so it's pretty interesting. It diverges a bit from everything that's been talked about in the session so far. It's not so information related, but more, I guess, transport psychology, but still, I think it's a very interesting survey design and study. So hopefully you also find it interesting. So first, I'll give some just brief information to talk about choice architecture. So this is from Thaler and Sestine, who brought the findings of behavioral science and policymaking into their book, where the concept of nudging was coined. So this is any aspect in the decision-making environment that alters behavior in a predictable way, but doesn't forbid any options or significantly change economic incentives. So it doesn't necessarily aim to change beliefs or values of an individual, but it tries to activate behavior and decision-making that is advantageous to society and also usually advantageous to the individual themselves. So nudging is part of this. This is the use of subtle interventions or prompts to change behavior. So this doesn't give hard measures, for example. It doesn't stop anyone in a transport situation. It doesn't stop anyone from entering a zone. It doesn't make anybody pay fines or anything like that. It just tries to make people change their behavior a little bit to hopefully have like more sustainable outcomes. So there are many different types of nudging. For example, default options is like when you are automatically enrolled into something when you sign up, like a health insurance plan. When you sign up with a new company, you have the option to opt out, but you're automatically put into it, so it makes it easier for you to stay into it. Use of visuals and salience, for example, would be use bright colors and be really eye-catching to make sure that safety warnings are like more obvious. There's incentives, there's framing, so like highlighting the benefits of a product instead of emphasizing what it's lacking. When it's like fat-free yogurt, that's the good thing instead of all the things that you're missing from the regular yogurt. Just some examples to talk about what nudging is, but I'm going to focus on social norms and moral appeals. So these two are the type of nudges that we used in this study. So the moral nudge is the benefits for the individual or the society. And the norm nudge is using social pressure and appropriate in-group behavior. So this is saying, oh, all of your friends are doing this, all of your neighbors are doing this, why aren't you doing this also? And then the moral nudge is, saying you could save more money by doing it this way. You could, have less emissions for the environment doing it this way. These are the main ones that we focused on here. And a big point of the paper and the research was to try to make the argument that it's interesting to have governments using nudges as a way to like complement their hard policies. So some examples of where choice architecture has already been used within government incentivizing, I guess, is in Stockholm, for example, with congestion pricing. This is very well known. In 2007, this started charging vehicles from entering or leaving the city during peak hours. So that's obviously disincentivizing people from driving if they can avoid it during those times. In New York City, they used calorie labeling. So this is a information or framing nudge. So it makes the information clear and accessible about the content of the foods. Another example, in Oregon in the United States, they use voter registration as a default option. So as soon as you get your driving license, you're automatically registered to vote instead of needing to do a completely separate process to also register to vote, and then getting people hopefully voting through this nudge. There are actual nudge units that have been developed in a number of countries, starting in the United Kingdom in 2010. The Behavioral Insights team was, I think, the first one that was actually set up as a unit where governments were coming up with ways to nudge people in the right direction. But in the United States, Germany, Australia, Netherlands, Canada, Singapore, and probably potentially even more since then, a number of governmental nudge units have also been started. And I think a main issue that people think about here is like that maybe nudging is some sort of like form of manipulation, but in the way that they're setting up these nudge units, they're being very open and very, very transparent about what they're trying to do. So I don't know that the manipulation argument is necessarily so strong, because if you know you're being nudged, are you actually being manipulated, or are you just being pushed a little bit to make better choices for you and for society? So a little bit about Flanders and Belgium, where we are and where we did this research. There is no nudge unit in Flanders, though there are pleas to establish one. It is something that people are thinking about. So there have been local governments that have set up different projects on their own initiatives with like external partners and consultancy companies. This has mostly been, though, in the context of like health. So putting good food at eye level and putting chips and bad food a little bit higher up so people don't necessarily see it immediately. Like these types of nudges have been used in Belgium. Nothing thus far in a transport context that we know of. Although we think it could definitely be useful in Flanders. And because of that, a little bit about the transport context for those who aren't familiar. So we are in the northern part of Belgium. It is quite known for its urban sprawl, which has led to a high car-dependent society. So it's quite polycentric within the cities. It is like kind of 15-minute city context. You have most of the things that you need available to you, but once you start to get into the villages, it gets a little bit more difficult, and the public transport becomes quite ineffective outside of cities. Another thing in Flanders that's exacerbating this is that because of the high tax rate, a lot of companies rely on company cars to then not have to pay as high of wages, so that they're not then taxed on those higher wages. So instead they provide company cars, which of course exacerbates the car dependency and makes people have no intention of choosing public transport, because why would they if their car is free and their fuel is free? But on the other side of that, there's a great cycling infrastructure relative to most places. I think maybe the Netherlands, Copenhagen, they're doing better, but cycling infrastructure in Belgium and Flanders specifically is quite good. There's also quite a big cycling culture. I think in where we are in Ghent and maybe all over Flanders, it's about a 30% of the mode share for all trips. So it is quite high. They grow up cycling. They're quite used to cycling. So nudging people to use their bicycle is not unheard of. And they also have quite strong environmental values. So Flemish people in general are quite open to making sustainable changes if they see that it could actually have a benefit in using public modes, active modes, car sharing, this type of thing. So in the most recently, or like in a way to get people to choose sustainable modes, policy has mostly focused on hard measures. So this is like pricing mechanisms, circulation plans, low emission zones, things like that. But they haven't really focused on these soft measures. So I'm hoping that, this type of research can start to come into some policy, and the behavioral insights can help policymakers to maybe better understand human behavior. So what did we do with the study? We had an online survey that was distributed through Facebook mostly, and snowballing in Flanders. And this asked the respondents about their different trips when they go to the store, works for hobbies, family and friends, go to the doctor and the dentist, and overall. I mentioned that here because through all of the statistical tests that we did, there was no difference between trip types. So everything gets all put together after this, but we did ask, we just didn't find anything different among them. And we had a response of 292, which is not super high, but it was a master's thesis, so we weren't really aiming for like thousands of people necessarily. Our survey, so the nudge was integrated within the survey. So this is how we set it up. The respondents started the survey. They had their informed consent, which told them that they would be nudged and explained nudging slightly to them. So they had an idea that this was going to happen to them. The pre-nudge phase asked them about their interest in using active travel, public transport, and car sharing for those different trip types. And then they were randomly allocated into one of the different nudge groups for their intervention. So half of them randomly got the moral nudge, half of them randomly got the norm nudge. And then after the nudge, they were then asked again within the same survey, the exact same questions about their interest in using active public and car sharing modes. So there wasn't actually a real intervention. We didn't actually see if their behavior changed, but it's just about whether or not their interest in using those modes changed due to the nudge. And we also asked about their attitudes toward the different types of travel and, of course, their socioeconomic demographics, with the idea that all of this information can feed into this kind of soft policy toolbox to complement the hard policy toolbox of the municipality, hopefully ending in sustainable behavior change. So those in the moral nudge group, they saw these 3 infographics, and they also had a little paragraph kind of explaining what it meant. And these, we were just, they're just hypothetical situations. We made them up. It's not necessarily like correct numbers, but basically we told them that walking and cycling makes you physically and mentally healthier. If you travel for 30 minutes a day, you have less stress, lower risk of depression, you weigh less than a motorist. Active commuting reduces your number of sick days. It improves your blood pressure. You're less overweight. You have less susceptibility to type 2 diabetes. All of these things. It's also more fun and it's cheaper. You don't have to sit in traffic jams. You don't cause air pollution. Better quality of public space. It saves you money. Then they also got the public transport nudge. So the benefits during the ride are all the things that you can do while you're on public transport. The benefits to your health. And then also benefits like through CO2 emissions for your health and the space that you're not taking when you choose not to ride the car. And with car sharing, the impact is that cars are less frequently used, there's less ownership, there's always parking spaces available, there's always a vehicle available for your situation. You can save lots of money, you can meet new people in your neighborhood, and you contribute to better air quality. The people who got the norm nudge just got this one infographic of a hypothetical household transport report. So this is saying the Flemish government looked into this and you use more CO2 than your neighbors. This is how your neighbors travel. They use public transit more often. They walk or cycle more often. They use car sharing more than you. If you did this, you would emit 26% less CO2. So they got those 2 different norms, and then they went back and answered the questions again. And we looked at the differences between the pre-nudge and the post-nudge answers with just really simply with paired sample t-tests to see if the interest changed in using car sharing, active modes, and public modes. And then also looked a little bit deeper, controlling for attitudes and socioeconomic demographics with multiple regression models. So quickly, just over the sample, we had an average age of 38.5. They were slightly more female than the average, which is 51%. So 62% of respondents were female. We see that a lot in our surveys, our online surveys. I don't know if women are just more like open to responding to Facebook surveys or they want to be more helpful or something, but we see this really, really consistently. Almost 70% are university educated, which is actually not too much higher than the norm in Flanders. 44.5% were employed full-time, which is quite low. So normally it's about 80% that are employed full-time. So I guess this includes, retired people, students, people working part-time who maybe have more time to take surveys online, this type of thing. And 20% of people had children at home under the age of 12, which we asked because that can quite substantially change whether or not you are interested in using car sharing because you might have to take a child seat with you, whether or not you're going to cycle because you have to cycle along with small children, or if you're going to walk, it's maybe less quick to walk with someone who's very small. the general attitudes regarding car sharing, active modes, and public modes, you can see that active modes were very, very high overall, but also very high for safety, relaxing, attractiveness, and preference. So this already indicates that the Flemish population, or at least the population that we surveyed, really has they're very open to active modes. So maybe they already do use active modes as well as a car, things like that. Public modes were next, not quite as high, but still quite positive, less attractive and not really their preference. And maybe not so relaxing, but in terms of safety and overall benefits, they saw that there were benefits. Car sharing, even less so. So they saw that there were overall benefits, but they didn't really think of them necessarily as safe, relaxing, attractive, or being their preference. So that kind of gives you an idea of where they were at going into these nudges. In terms of the paired sample t-tests, we saw, so this, the closed boxes means that they were statistically significant. The open box, which is just that one on the norm nudge side for car sharing, that was not statistically significant. So there were some significant findings. For car sharing, we saw that the moral nudge was very effective, particularly compared to the norm nudge, but just on its own as well. So I think that this just indicates that people don't really know that much about car sharing and the benefits yet. So when you do introduce them to like, oh, there are all of these benefits, you can save this money, you're doing this for the environment, then it's maybe it becomes more interesting to them to have more information. People were quite, similar with the moral nudge and the norm nudge in terms of active modes. They're probably already likely to be open to using active modes. So the nudge, I think the efficacy is not so high and maybe more similar because it's something that they already know. And then with public transport, it seems that the norm nudge is quite high compared to the moral nudge. So I think this indicates they already know the benefits of public transport. They already know that it's more sustainable. They already know they can save money maybe, but until their neighbors start doing it or their friends start doing it, that's when people start to follow, as it becomes like really the normal way to travel. And then when we looked a little bit further into the multiple regression models, we found that, so I'll start in the top left corner in terms of the moral nudge for car sharing. People with better attitudes toward car sharing were more susceptible to the moral nudge, which makes complete sense, I think. They were also more susceptible to the norm nudge than the rest, but particularly for the moral nudge. This came out. So yeah, it's just kind of telling us what we already know. If you get reinforcement about the information that these are good ways to travel, then, and you already have good attitudes about it, you're more likely to use it. Again, people without children were more susceptible to the moral nudge. So I think this again shows that people with children are less likely to want to use car sharing just because it's a hassle to try to find a car. If you have to do multiple trips, if you have to drop off at daycare, go to do groceries, go to work, you're not thinking about carrying car seat around all day. In terms of car sharing for the norm nudge, people who were younger were more susceptible to the norm nudge. So I think this could also indicate that younger populations, like maybe young 20s, people coming into starting to drive are more open to car sharing, potentially because it's cheaper, but also because they've been growing up hearing about the sustainability benefits of it. And like, instead of buying a car, maybe they can just inscribe into a car sharing system. In terms of active travel, women were more susceptible to the moral nudge. Research shows that women have they care more about the environment. Maybe not in all cases, I'm not calling out men, but this could just show that women again already realize that there are benefits for themselves and the environment for active modes. So that's how the moral nudge can just reinforce that. And then those without a driving license were more susceptible to the norm nudge to use active modes. So I guess this could indicate, although I don't really see it in Flanders, but with some sort of stigmatism for not having a driving license, or maybe for needing to take a bike to work because you can't drive, the more that people start to do it, the more that it becomes normal, the more open people are to it. And then in terms of public transport, people with higher incomes were more susceptible to the moral nudge. So yeah, realizing that there are benefits for the environment, maybe that could get them out of their cars. And then people with better attitudes toward public transit were more susceptible to the norm nudge. So Yeah, in general, just to wrap it up, this is a very interesting way. This is really a first step. We want to go into the field and we want to do a real actual nudge scenario and try to do something to see if behavior actually changes. But this already indicates that these types of nudges can be effective in getting people out of their cars toward car sharing, active travel, public transport. Of course, these nudges or these soft policies can't be used alone. They need to be used at the same time, complementary to the congestion charging and the low emission zones and these kind of hard policies. But these are all different ways that we can work together to try to push this sustainable behavior change. We had this paper published recently in Transportation Research Part F. So if you want the code, I think I have a QR code on the next slide for it. And yeah, thanks to my co-authors, Juliet and Frank. I'm happy to take some questions. Thanks again for listening. Oh, I think you're muted.
I'm sorry. Thank you so much for the great presentation, and we need to wrap up real quick. We do have 2 questions in the chat box. Where within the government structures are these large units located?
Say it again. Sorry, where?
If you can read the question in the chat box. Where within the government structures are these lodging units located? Are they within specific transportation agencies?
That's a great question. Juliet did the research on this, so I'm not 100% sure. I think that they are separate agencies because they're looking into kind of like the health nudging as well as the transportation nudging, as well as whatever else they can come up with. So I think they then feed and communicate with the transportation agencies about the nudging, but I would need to look it up to be 100% sure on that.
All right, the last question is is this research applicable to other major cities or of this country, Bangladesh?
Yeah, I think definitely. In Ghent, they're very open to cycling and open to very open to sustainable transitions. So it's going to be particularly effective here. But I think the more that you start putting it into different cities, not even in Belgium, but anywhere, you can start to nudge people and it can start to catch on, and it can be like a way to push a little bit and maybe make up for places where the hard policies aren't so strong.
All right, thank you, Hannah. I think that's all we have for this session, and thank all the speakers. And now let me just take 1 minute to kind of introduce the sessions in the afternoon. We have 4 more sessions. Session 11 is a special session talking about the open science in transportation research. And session 12 is a future mobility landscape and data. And then session 13 is about user choices